Hello, my name is Ray Watkins here, and this is our CAP number one assignment, ATP pathways. So what I want to do is I wanted to start off first with an overview so we can understand, what are we trying to accomplish here with this CAP assignment. So I chose the first two questions that I always like to start off with is what are we doing and why are we doing it? So what we're doing here first is we're going to be talking about the catabolism or the breakdown of a glucose molecule and one fatty acid molecule, specifically palmitic acid, for energy transfer. Now, I like this term energy transfer because it has a basis in that first law of thermodynamics, whereas energy cannot be created, neither destroyed. So the main concept here is what we're doing is we are taking the energy from foods that we ingest or intake, and we're going to transfer that energy through our body in multiple processes to do work. And that is why we're doing this here. Our body is in need of energy for biologic work, for mechanical work, chemical work, and also transport work for certain activities within the body. So it's really important that this system works for us. And this is the main reason why we're doing it. So what I've put here is the overall, diagram for both glucose and a fatty acid metabolism. The reason I like this here is because what these both pathways have is they share certain components, but they also have certain components that are specific to each of them here. So as we can see through here on the left-hand side, we have our start off of glucose here, a molecule of glucose, and then on the right side we have the substrate of a fatty acid. So those are the two we're talking about. But what they do is they share some common processes here, and they also have some processes that are individual to them. The individual processes for fatty acid is going to be this beta oxidation cycle here, and the proprietary mode of breakdown for glucose here is going to be glycolysis, which we will get into a little bit later. But I wanted to show that relationship that they have those individually. But down here, we have our citric acid or Krebs cycle and the electron transport chain and oxidative phosphorylation. Now, both of those are used in either the breakdown of glucose and a fatty acid. So there are two processes that they share and two processes that are specific to them. So we're going to start off first with the energy transfer from the palmitic acid or the fatty acid. So starting off first here in the diagram here in the yellow highlighted section, since this is proprietary to the fatty acid, our first process is the beta oxidation. So what beta oxidation does, it works on degrading this free fatty acid into a very, very special and specific compound called acetyl coenzyme A. Now, that acetyl coenzyme A is going to be used later in the next cycle, and that next cycle cannot go or be maintained unless it has this acetyl coenzyme A. So another byproduct of this beta oxidation is a hydrogen is released, and it's oxidized through the respiratory chain. So we'll get into where these hydrogen ions go, but those are going to be also some energy units used in the final production of ATP. So the beta oxidation takes the free fatty acid and it degrades into acetyl coenzyme A. And then we move into this middle section here, the Krebs cycle or the citric acid cycle. This acetyl coenzyme A that's produced through the beta oxidation is broken down through an enzymatic process, and it produces carbon dioxide and hydrogen atoms there. Now, it's something, there's about 10 enzyme processes that go on. And the main reason for this Krebs cycle is to produce as many of those hydrogen ions as possible, because those are going to be important in this next phase here, which we'll move on to the right here, is going to be the electron transport and the oxidative phosphorylation. Now, these are two different processes that help we get the final product of ATP here. So electron transport first is where we take these hydrogen ions and they pass through the mitochondrial inner membrane and into the matrix of the intermembrane space. So it's something where these ions cannot diffuse just through this membrane. They're going to actively be transferred over from the matrix into the intermembranous space. And that is where all the fun work is going to be happening there. So When we're in that intermembranous space, these hydrogen ions are going to find ADP, which is adenosine diphosphate, and the free floating phosphate groups, and that's what's going to be used to join those together. So the ADP plus a phosphate group using these hydrogen ions create ATP. So to review, we have the beta oxidation where the free fatty acid goes and is degraded to acetyl coenzyme A. Then that moves into the Krebs cycle. And in the Krebs cycle, that acetyl coenzyme A is broken down to produce these hydrogen ions. Most of them are produced in this Krebs cycle here. And then that moves through electron transport into an oxidative phosphorylation where the electrons are passed through a membrane in the mitochondria. And in that intermembrane space, they join ADP and a phosphate group to ATP. So now we have a similar but different process here for a molecule of glucose. So we're going to start over here with this process called glycolysis. Now, there's two different types of glycolysis here, and I want to start off first with anaerobic glycolysis. So basically what this is this is glycolysis that does not have oxygen associated with it. What this is glycolysis is this 10-step enzyme control process, and the main point of this is to turn glucose into pyruvate. Now, pyruvate is going to be another very important substance for glycolysis here. But what happens with anaerobic glycolysis is we're going to need oxygen present to go ahead and be the final acceptor for these hydrogen ions that are produced through the glycolysis. Now, if oxygen is not present, like this anaerobic example here, what happens is all these hydrogen ions are then bound with pyruvate, and then that builds up lactate. And the lactic acid buildup backs up, and that's when we stall and fatigue, and we cannot move into this next section here. So there is ATP production through anaerobic glycolysis, but it's definitely not as much as it would be through aerobic glycolysis. So now aerobic glycolysis here on the top is, like I said, a similar process. We have a 10-step enzyme process where pyruvate is derived from glucose. But now, since we have oxygen present, pyruvate is going to be turned into our good old friend acetyl coenzyme A. So we can see here where the presence of oxygen is very important, as if we're going to be producing a small amount of ATP in a short amount of time, or it's going to take more time and hopefully produce more ATP. So with this process, we now have, through aerobic glycolysis, glucose turned to pyruvate, pyruvate then broken down into acetyl coenzyme A and pyruvate oxidation. And then we can go through those last two steps that we went through before with the fatty acid. So we have the Krebs cycle or the citric acid cycle, where that acetyl coenzyme A is broken down and we get those hydrogen ions produced. And then those are shipped on over for electron transport and oxidative phosphorylation, where they pass through the membrane and they help join ADP to the free floating phosphates. And there we get ATP as well. So now what we're going to look at is the total ATP yield. So it's kind of how much bang for your buck you're going to get with each process here. So I wanted to start off first with one molecule of glucose through aerobic glycolysis here. So aerobic glycolysis, remember we talked about, that means having oxygen present. So we have the first two cycles with glycolysis through aerobically, and the Krebs cycle, or that citric acid cycle. The total net ATP produced, there are going to be 4 molecules of ATP. Now, total is 6, but to prime the pump and to get things going, it does take 2 molecules of ATP to get glycolysis moving. So we get a net of 4. Then when we move through the electron transport and we get to the oxidative phosphorylation stage, we get a total net of 28 ATP molecules. So we're moving down from glycolysis to Krebs cycle to oxidative phosphorylation, and our total yield for 1 molecule of glucose is going to be 32 ATP molecules. All right, next we're going to be looking at the same process of looking at the ATP yield, but this time through our 16-chain palmitic acid. So through beta oxidation, this 16 carbon chain is split and it produces a 35 ATP. And then what we have next is going to be the acetyl coenzyme A that is created through beta oxidation, going through that Krebs cycle and the oxidative phosphorylation. So the finishing touches of that fatty acid metabolism yields us 96 ATP. So we get a total of 129. Now, that 129 was 131, but again, similar to glycolysis, it does take 2 ATP to start that process in beta oxidation. So a couple things to talk about in discussion so we can finish up here. I wanted to talk about the pathways and how they intersect with intensity and duration. What I want to talk about is the relationship between those, whereas then it's an inverse relationship. So the higher the intensity, the faster the rate we need for energy transfer. So with those processes, we need to use a faster system to transfer that energy, such as anaerobic glycolysis or the phosphocreatine system. At lower intensities here, where the rate for energy transfer is slower, we can use aerobic glycolysis or even the fatty acid metabolism there due to the fact that we're not working at such a higher intensity. Now, there are several factors that limit this ATP production. Very similar to both of those are going to be oxygen, some hormones and enzymes, substrate source. So if we have enough carbohydrate or glucose molecules or enough free fatty acids coming from lipids, that's going to limit these pathways. But then also is the ADP concentrations. It's a very sensitive ratio that's set within the cells there, where if something goes off, if we need more or less, those systems can react real quick. Lastly, I want to talk about this real world application and especially why we cannot be dependent on one system working. The reason is that because both of these pathways interact at certain points and they work together, especially at this Krebs cycle or the citric acid cycle. That's that metabolic connection here. That for that cycle to run, it's dependent on certain byproducts from carbohydrate utilization there. So if carbohydrate utilization runs down or slows down due to depletion in substrates or so forth, fatty acid metabolism will slow down as well. So one system does not work independently without the other. So if we have a marathon runner here and who wants to run 26 miles there, you would think, man, I've got a lot of fat on me. I can just use that as my main energy source, and I shouldn't have to slow down. But the thing is that fatty acid metabolism there cannot go because it is limited by, or it is burned and started by the carbohydrates. So hopefully we get this real world application here and we can get these processes down and how important they are to the human body. So we can go from, the food that we eat to the work that we do, and we can make that connection. And such a wonderful thing to know that this body was created to do such intricate work here. So I hope that helps you out. Thank you very much.